All right. As introduced, I'm Robert Kubis. I work for the Google Cloud Platform as a developer advocate. We understand ourselves as being like a bidirectional connection of you guys into our organization, into our developers. So you find here my Twitter handle and also on GitHub, and you find me on Medium and other channels as well. So if you have really cool ideas, if you have constructive feedback, what we can do better, things like that, please feel free to reach out to me. So what am I going to talk today about is Google Dataflow and Apache Beam. But before I dive into this, I want to actually go a little bit into the history. So how did that all evolve? Like if you go roughly 15 years back, it's 2002, Google has been like 5 years old roughly. And our mission was to make information accessible. Right? And so you can imagine there's a lot of data that we had to process every day, and the conventional tools just wouldn't keep up with that anymore. So our developers, basically were looking for new ways, and each of our developers were basically doing similar work. So Sanjay and Jeff Dean, which are our like super smart fellows within Google, they came up with a framework how to process large amount of data on commodity hardware and commodity storage. So that was basically the start, which was published as the MapReduce paper in 2002 or 2004, and kickstarted the whole like ecosystem and world of big data processing. So just to get everybody on the same page, what is MapReduce about? It's a very simple way of processing a large amount of data. So basically, you have your data. You want to extract some key out of this data, so basically you have a map function which maps each element to a key and some data, and then you have a shuffle process which basically then shuffles the data to so-called reducer machines, and these reducer machines, based on the key, basically do aggregations. So now that model is very powerful. You can pretty much every data processing algorithm put into the MapReduce, but you might have to modify your algorithm beyond recognition in the way that it's like you write it once and never anybody can read it again. So that's basically the first stage. But the problem of this was that now developers started running more and more MapReduce jobs, but there was no way of like gluing them smartly together. So basically, they ran one job, then copied data from one place into another place, and then run another MapReduce job. So basically, what we needed is some way of formalizing and on a higher abstraction ways to process multiple steps in your data processing pipelines. So multiple MapReduce jobs. And that's where Flume Java comes in. So Flume Java gave us this higher level API to basically logically process your data in multiple steps from like your source to your sink. And if you look at how that looked like basically on code is you have like this logical view, the logical steps that you would choose to process your data. You basically first have to select an input source. In this case, we do the mean computation of temperature, and we have, for instance, like here the raw data which is coming in from like BigQuery or from cloud storage or any kind of place, maybe files as well, right? And then we have like our parse function, which is the map function, which basically extracts the key. And then you see down there the mean.double per key basically does the grouping and calculates the mean of that like per key. And then we write it out to like Bigtable or files again or things like that. And you can glue them, multiple of these things together. Now, we taught like our developers, like a lot of the nooglers, like Flume Java, and they all started processing a lot of data with Flume Java. So a lot of Flume Java jobs were written. But as you can imagine, data is big. Data is actually really big. And it's really difficult, like, how do you process all that data in a smart way that you get insights to your data quickly, but still process like correct results? So there are a couple of problems with this batch mode of processing. Like you saw in the slide before, what you can do is, for instance, you can chunk your data by day, for instance, or by hour if you have log data. Now, the first problem with this is latency. So if you chunk your data or split your data by day, for instance, then you run your batch job all the way always at the end of the day. You have to basically always wait up to 24 hours and plus the processing time till you get insights to your data. So there's like a high latency to that. The next problem that we see is usually like your data that you collect doesn't adhere to these artificial splits that you're setting there. Your data is not like it stops at the end of the day and then begins at the next day again. So for instance, if you have a 24/7 business all around the world and you want to get insights into your user sessions of your users that are using your products, these will go beyond like these artificial splits. So basically, even though you use batch, you might end up with incorrect results because you're splitting the sessions. And so if you really look at the data, what we have is not like this batch-like kind of data. What we really have is a continuous stream of a lot of data, and which is unbounded. And the next problem, it's usually also delayed, some of your data. When is your data delayed, for instance? So imagine you have an application like an Candy Crush, for instance, and your users go on a plane and go in airplane mode and play the game on the airplane and then step out in San Francisco or somewhere else 10 or 15 hours later, and they turn on their phone and all these events suddenly trigger into your system. Now, these events happened actually at a different point in time than they arrive in your processing system. So you have to account for this delay. So how did we deal with like this unboundedness and like this large amount of data like that? It more comes in a streaming fashion rather than like in batches. And that's where we came up with MealWheel, which is again also in Java, and it basically you construct a directed acyclic graph. So you basically write computations and transformations in a graph, and the system takes care of setting up the machines and putting your data through the different stages in a streaming fashion. So what are patterns that you can do, for instance, in streaming fashion? Very simple. First one is filtering. So you get a lot of data and you filter like a couple of data out based on certain criteria. And then, of course, you want to basically window your data. You want to put it in some kind of container where you can then do aggregations on it. And that container can have different kinds of shapes. It can have like session shapes. It can have like time-based shapes and other things. Now, if you look at these two systems, so if you look like at batch processing and stream processing in like more like the state-of-the-art systems, so there are a couple of things that you have to do trade-offs on. I picked 3 criteria here that I want to show you some use cases where you basically, if you look at the state-of-the-art architectures, where you choose either a streaming system or a batch processing system to get your results. So first one is completeness, so that you get correct results out of your data that you process. So if you want to calculate bills or something like that. Second one is latency. I talked about this already, like if you do batch processing, you have a certain amount of latency depending on the size of the chunk that you set. So sometimes you want to have more recent results, so that where latency comes in. Third one is cost, like how much money do you want to invest in your data processing pipelines? And that's like basically you have to weigh that in with the other 2 criteria. So let's go in a use case. The first use case that I want to talk about is a billing pipeline. Now in a billing pipeline, it's really important, and you see here on this graph we have on the y-axis not important at the bottom and high important at the top. Which is really important here. I just want to point it out because it trips up a couple of people, myself included. A low bar in the low latency doesn't mean low latency. It means low latency is not important. Okay. So in a billing pipeline, what you want to have is you don't want to overcharge your customers. And you don't want to undercharge your customers either, because that's bad for your business. So a billing pipeline, it's really important that your billing pipeline is correct. So cost is not really important in that case, because you want to be correct. You don't want to offend your customers, and you don't want to lose money by miscalculation. And low latency is not that important either, because it's fine if your customers wait like a day or 2 till they get the final bill for a month. Now, what is nice to have for your customers is that if they see a runway where they are going to in terms of their bills. So if you want to do live cost estimation, you actually want to have that like basically in the moment they are looking at it, and it wants to be like very like recent. But it's not so important if there's like a cent or maybe $1 of difference at the end. You make your like billing and at the end with like a batch pipeline, for instance. But the completeness is not like that crazy important. You want to be somewhat in the ballpark, but it's not crazy important. And low cost is really important there because you don't want to burn all your profits in running this live cost estimated pipeline. Now, a third use case is abuse detection pipeline. Now there, it's again, you want to like, it's good for your business if you detect abuse early on and you can counteract abuse because you don't lose money in that case. So low cost is not that important in that case. You might want to invest some money to have a good abuse detection. Now, completeness is not that important either. It's somewhat important in the sense of like, of course, you don't want to offend your real and proper customers that are nice ones, but you want to keep away the abusive customers. Low latency here is really important because like as sooner as you detect abuse, as more money you can save, right? So now if you look at the state-of-the-art architecture, like all of these three pipelines that you saw can basically be fed off like similar data or even the same data to some extent. Now if you look at state-of-the-art architectures, what you basically end up with is two systems. On the one hand, you have like your batch processing system for correctness, and then you have your stream processing system for estimate and approximate. So for instance, for batch processing, you look into like Hadoop, Spark, things like that. And then for stream processing, you look in like Storm, Flink, things like that, or like even Spark with micro-batching. Now, what that means is that you basically have to learn, your developers have to learn two systems. Right, so you have one group of developers that do the batch processing, and then you have another group of developers that does all the stream processing. All right, so you end up with duplicate work. You end up with like needing more skill sets to actually come to the results that you would like to. So that's where Dataflow and Apache Beam comes in. So basically, Dataflow took all the experience that we gathered from starting from MapReduce through Flume Java and Mealwheel and packaged it up into a fully managed service and an SDK where you can write your pipelines, your data pipelines in a higher abstraction. And the nice thing of Apache Beam and Dataflow is we basically donated Dataflow to the Apache Beam Foundation and became a high-level project this year, actually beginning of this year, is basically we enabled portable data pipelines. So let me go in a little bit more detail about this. So Apache Beam allows you basically with the SDK that we donated to open source to write higher-level parallel data processing pipelines. And then run it on different kind of runners. So it's possible to run like Apache Beam pipelines, for instance, on Spark. You can run it on Flink, and you can, of course, run it on Dataflow, which is our fully managed service. Now, I want to like ask everybody, so I want to show a little bit of code. My title is Developer Advocate, so I have to have a little bit of code in my talk. And I brought here a live demo that I've run at a couple of events. It is very simplistic, but I want to show you basically that I use the same methods, the same functions to process my data in stream and in batch processing. So what is this demo about? It's very simple, and you can pull out your phones if you want to and scan that code. I also have that code, that QR code, at other slides if you miss it here. But basically, this app is very simplistic, and it doesn't collect any like of your private data, just that being upfront. What I collect is basically you get generated a user ID, you get assigned a team. It's 4 colors, so we have blue, red, green, and yellow, I think, as the colors that you can play for. And it's basically calculating, like you have to, like we switch the colors of the 4 positions, and you have to basically tap on your color, and we calculate like a team score and a player score, like how accurate you are in tapping the right color. Now, what we collect is basically a user ID if you tap the right color and which team you belong to. And I'm going to show you the data in a bit. So what I want to achieve with this is 2 things. I want to achieve with this, on one hand, correct results, but also like streaming results. I want to give you feedback like really quickly. So you basically start playing it, and after 10 seconds, you see like your own score, and you see the score of other teams and things like that. So this is the pipeline that I'm running for this game. So basically, you have your mobile app or desktop where you play the game. That goes into PubSub, which is our fully globally managed, scalable messaging system. That goes into Dataflow, where I collect this data and basically window that data and aggregate, and then I push it out to PubSub and BigQuery again. So now to do this, to have like correct results, I have to ask a couple of questions. And I want to start here. The first very important things to get correct results with Apache Beam and Dataflow is a differentiation of two things. One is the event time, and event time means like when did your event actually happen. So back to that example that I gave with the game in the airplane. Right? If you basically crush your candy, that is the point when an event actually happened. And processing time describes the point in time when the event is received in your infrastructure to process and aggregate the data. So we have to differentiate these two things to be able to actually calculate correct results. So here in this example, Candy Crush, for instance, I have this dashed line there, which is our real-time line, basically. If you find any events on the lower right part of this graph, please find me afterwards. I get you a good paycheck. What does that mean if you find an event in the lower right part? It basically means you know an event will appear before it actually appears. So you process an event before it actually happened. And if you can do that, please find me afterwards. We didn't do that yet. So basically, when an event happened right at that dashed line that you see there, that means that the latency between the event happening and the event being processed is very low. Now, if you find an event very like to the left, basically very far away from that dashed line, it means that the event happened way earlier than it actually was coming into our systems to being processed. So that are the 4 questions that we ask to get the correct results and steps through this data in a streaming mode. Is first, what are we calculating? So that is a very familiar question from MapReduce. So what are you doing with your data, like filtering, group, things like that. Second one, where in event time are results calculated? So that is basically when did that event happen and how do I group the data together so that I have to get correct results? And I go in a little bit more detail in a second. The fourth is when in processing time do I do something with the data that I calculate? So that basically means when do I emit any data? When do I put results down to my downstream systems? And a fourth question, which is really important, is how do I relate, what do I do with refinements in a way, like what happens if data comes in delayed? What do I do with this data? And how much late data do I allow? So going in the first question, very basic, what we can do with our data is basically filtering, parallel filtering, aggregation, and the composite of all this. So if we do this in our example here, we basically read the data from some raw log, from a message bus, for instance. Then we do an extraction of the key. In this case, we extract, for instance, the time when the event happened, so the event time. And then we collect it together into and aggregate, or basically here what we want to do is we extract the team, not the time. We extract the team so that basically we can group by team, and then we calculate scores by team. So what that looks like is basically here, what you're familiar with, that's the batch processing. We still have to wait till the end, till we processed all the data. So we have gained nothing in terms of latency. So we still have to wait, and we have a high latency to emit results. So now, what we have also, first step to get to lower latency is that we want to have basically, we want to chunk your data a little bit up so that we get more fine granular results. So there are different ways what you can do. You can do fixed windows of time, you can do sliding windows of time, and you can sessions, for instance, session windows. So in my example case, I select the session of 2 minutes. I chunk my data up in 2 minutes and aggregate basically over these 2-minute windows. So what we end up with is basically now that we have these 4 buckets, and we calculate the results for these buckets. So we have a little bit more fine granular, we know which team was leading 12:01 and which team was leading 12:03, but we still have to wait till we processed all the data. So we have to go a step further. And that is basically where the event time comes in. and the split between event time and processing time, where we basically say, okay, when in my processing time am I confident that I have all my data for a certain bucket of event time? So in this graph, which is shown again, the dashed line is our real time. And that red line that you see there is basically our delay that we have. And we call that like the watermark. That is basically the reality when data comes into our system. So if you go, for instance, let's see if that works. So if you go here, for instance, like we have our processing time, which is like here, let's say that it's 12 or 5. And we have at that point, we have all the events till 12 or 4 instance, right? And so we have a delay of 1 minute. So at that point in time, we're confident that we have seen all the events till 12 or 4. So at 12 or 5, we can basically say, okay, we passed the watermark, and now we can basically say we trigger to materialize a result. So that watermark can be heuristic, it can be given by your sources and things like that. So now, in my example, what I do here is I basically say, okay, once I pass basically my 2-minute window of event times, once I'm confident that I have all my elements in there, I want to emit a result. So what we see here now, like we see the watermark going up, which is this green line in this case. And once we pass, like our processing time passes the watermark, we emit a result. And now you see already, okay, now we come into that region where we actually can emit results much closer to when the events have happened. And it becomes more lively and more real-time to get insight into our data. But as you can see also there, we are missing. This is still not correct. The data that we calculate here is basically, to some extent, estimated data. And the reason is that you see there the element number 9 is not considered at all. It's outside of that point where we emit result for the bucket number 1. So what are we doing with this data that comes in late? And that's where the fourth question comes in, so how do we refine? So basically what we do is, in this case, you see here we want to have, on the one hand, like data being emitted like a little bit earlier. So right now we emit the data after the watermark passes, which can be more than 2 minutes. And if we want to get like some estimates, we basically say like, okay, please emit a result every minute already. So that's what I say here with early firings of my triggers. I basically say like, please emit the data already after a minute, each minute. And what that means basically after processing time is basically once like it starts processing that window, immediately at that point, basically it starts emitting every minute. Now, another thing that I want to do is I want to do late firings. So basically when a late element comes in, right away when a late element comes in, I want to already push a new result for my window out. But now what I have to do is I basically have to define like what am I going to do? What kind of results do I push downstream from my calculation? And there are two different ways what you can do is on the one hand you can do accumulating fired panes, which basically means you keep all your data in memory, and when a new element comes in, you calculate the entire window again and push the complete aggregate again. Now another option that you have is so-called discard fired panes, which basically means once you have emitted a result downstream, you basically delete that data and you only calculate differences and push only difference downstream. Now that is not always like possible, so you have to see case by case where that is possible. Now there is one thing which is really important here, and that is the with allowed lateness. And the list with allowed lateness basically says, like, how long do you keep a window in memory? Because if you would keep it in memory infinited, you basically would run out of memory, right? So at some point you have to close. You have to close a window. You have to discard it and write so that you can free up some memory. So this is basically your boundary where you say, I keep it for another 10 minutes open. And if after 10 minutes nothing, like if then something comes in, that is basically discarded. And if you think of it, for instance, now some might say like, oh, like this could lead to non-exact results. But if you think of like your billing pipeline, and you chunk them up by day, and you can start calculating after the end of the day, everything which comes after that is also discarded, right? So it's not 100% exact either. So it's basically the same semantics there. So now if we look at this, basically we have these early firings, as you can see here, after a minute. When I start that window, after a minute, I start early firings. And then you see the on-time firing, which basically says, like, OK, I believe I passed the end of this window. My watermark is passed, so now I emit a result. And in the case of late arrivals, here in this case, I basically emit a new aggregate for that window, which is in that case 14. All right. So with these 4 elements that you just saw, we basically went from a classic batch processing through windowing, through streaming to accumulation, and how to work with late arriving data, how to get estimates and things like that. And I want to show you that really quickly, how that looks in my code. So what I have here is, let me see, I have like a streaming pipeline here, which is basically that game that you hopefully played a little bit. And let me start the batch pipeline really quick. To start this, because that takes a little bit till that batch pipeline runs. So basically what I do is I read my data from PubSub, as you can see here. Just very normal, like I have a topic and all the data that when you click, it goes into that topic. Now the very first thing that I do, which is a good practice to do, is like take the data, unfiltered, and store it somewhere where you can process it at a later point in time, unmodified. And then what I do is basically, when we ask the question, like, what am I calculating? I do calculate a couple things. I calculate the team stats, like what is the team doing, how good is the team. I calculate the player stats, as you can see here. And that is pretty much what I do for this. So let's have a look at, and before, like, to get basically these aggregations, I have to do 2 things. For my team stats, I basically have to key my data by the team that you're playing. And it's pretty simple. I basically go into my stream, get the team information, and say, OK, this is my key for that element. So basically, I get table rows in, and then I just go in this table row and say, like, hey, what is the team? And that I emit as a key. Very simple. Simple again for the player. When I want to have the stats per player, I go into my table row, I check the user ID and pull that out and basically key my data by a user ID. And the last thing that I do is calculating the team stats, for instance. So we have here the team stats where I go in. Is that the right one? This is writing, that's not calculating. Sorry about that. So basically here in the team stats, I calculate, I basically go through what my data is in my window and go through and calculate things like hit rate, if primary mobile, and when this result was actually calculated in terms of, here you see that firing is basically, I give the information down to my sink, like what kind of trigger firing that was. And it's pretty simple and the same for the player stats. So now if I go to my streaming pipeline, we know what we're calculating. And now like the other 3 questions for my example is that I want, on one hand, where in my processing time where in my event time am I calculating? So here for my demo, I choose 5-minute windows. So everything which happened within 5 minutes of event time is aggregated to get the team stats and the player stats. Now, I don't want you to wait 5 minutes till you get any results. So what I'm doing is I am emitting actually elements every 10 seconds. So you see here, once the window has started to process elements, every 10 seconds I emit results so that you see like what your player score is and what the team score is. And then I also allow some data, so like some late data. In 10 minutes, basically, I say like it can up to 10 minutes elements come into the system and still are being processed and then emitted as a result. Now, if we look at how that looks like, in Dataflow, we basically have this streaming pipeline here, if the Wi-Fi holds up. And you see here, like we're reading from PubSub, we are windowing the data, and we are writing everything to our BigQuery. And then we basically are calculating by team and calculating the statistic per player. Now what also you can see is we have this batch running here. And it's still running, unfortunately. It says all succeeded, so let's have a look if it actually succeeded. So what you see here is BigQuery, and BigQuery is our data warehouse, which is basically you can crunch terabytes up to petabytes of data in seconds or minutes, respectively. So what I'm doing here is I calculated in my batch pipeline the overall team scores from all events that I captured over many, many events that I have done so far with this demo. And to go back really quickly to show you what the batch pipeline looks like, it's very simple. I'm using exactly the same elements, so you see no additional code here. I'm basically running my batch pipeline with the code that I have written for my streaming pipeline. And what I removed is just the whole entire thing of like windowing and processing time and triggers, since when I'm processing in batch time, I don't need these elements. So let's run this query, and let's see how much overall what the rate is. And we see some new data coming in here, which looks pretty good, 12:57. Yeah, we are 2 hours ahead of UTC, so that is actually pretty live. And as we can see, red is the all-time winner. So everyone who was in the red team, congratulations, you are the part of the winning team. With this, I want to thank you, everyone. I want to show one more thing, if that loads, hopefully. So I mentioned one thing about Apache Beam. If you write your pipelines in Apache Beam, you can run them on multiple runners. So here, if you go to beam.apache.org, you can find a runner capability matrix where you can see if you write your pipelines in Apache Beam on what kind of systems or frameworks or runners you can actually run them. Right now, you have Dataflow, Flume, Spark, Apex, and Gearpump as the runners that are available. And with this, thank you very much for your attention. I hope it was not too rushed.
Yeah.
Wow, on time.
Yeah, it's perfect.
German accuracy.
Yeah. Genauer Punkt. Well, yeah. out of respect, we actually have 3 quick questions out of respect to those who place. And these are actually quite easy to answer. And then we will have a 15-minute break before we have our next speaker. But the first question was, how do you do error handling, especially with streaming workflows?
Yeah,
that's from Patrick.
Yeah, so they're different. On the one hand, you can basically have outputs where you put your error data, and then you handle your data differently. On the other hand, you can, of course, you have all logging, so you can inspect how your pipelines are running. But it's always a good practice if you have data which basically doesn't conform in the pipeline that you're working with, that you drop that data unfiltered somewhere so that you can work with this data at a later point.
Cool. Second question from Christian. What's the recommended approach on Google Dataflow if you strive for zero downtime deployments?
Oh, very good question. So Dataflow is a fully managed service. So zero downtime, basically what you want to have, of course, is multiple workers. So you definitely want to have, you recommend at least starting with 3 workers. That is one thing. The other thing is what you want to enable is auto-scaling. So be able that if you suddenly have more data coming in, that this data can be handled through your auto-scaling cluster. Now, if you work, for instance, what you also want to be sure is that you worked with systems before Dataflow that basically can handle a burst of data so that Dataflow can basically ramp up new machines and then can basically back process the backlog that built up. So PubSub is, for instance, one system which allows you to be available for data pushing all the time, and your Dataflow cluster can scale by demand.
And last question from Marcus. Can events be written to disk to further extend possible latency?
Say again, what was the question?
Can events be written to a disk to further extend possible lateness of events? So,
I'm not sure if I understand that that question correctly.
Are you talking about caching? Maybe caching to disk?
So events can, of course, you have multiple ways of processing your events. Dataflow is one of them. If you, for instance, use PubSub or any kind of other message bus, you can have multiple consumers on your message bus. So you could, for instance, as I showed from the pipeline that I had, I write these unfiltered events to BigQuery, but you can also write them to disk or things like that. But I don't know how that plays into extend possible lateness. So maybe we can clarify. Maybe come up and clarify that question.
Let's give a warm applause to Robert Kubis from Google. It was a wonderful talk. Thank you so much.
Thank you very much.